There is an element sitting inside the ground beneath your feet right now that has been slowly releasing heat for 4.5 billion years, that once accidentally assembled itself into a working nuclear reactor with no human involvement whatsoever, and that we used to paint children's teacups with before we had any idea what it actually was. One element. And the story of how it got here is so extreme that scientists spent decades arguing about whether it was even physically possible. Let me start not at the beginning, but at the moment everything got strange. A processing facility somewhere in Central Asia receives a routine shipment of uranium ore. Standard procedure. A technician runs the isotopic analysis, the same measurement done thousands of times before, expecting the same number that always comes up. The same number found in every uranium sample ever tested on Earth, in moon rocks brought back by space missions, in meteorites that fell from the sky. That number never changes. It is as fixed as the speed of light. Except this time it does change. The ratio is off. The technician checks the equipment, recalibrates, runs the test again. Same result. He puts the report on his supervisor's desk and goes home that evening with a feeling he cannot quite name. Something between confusion and the quiet suspicion that something much bigger than a calibration error has just walked through the door. That anomaly, that single number sitting slightly wrong in a column of data, eventually pulls scientists all the way back to a question nobody expected to be asking. Where did this element actually come from? Not which mine, not which country, not which geological formation. Where in the universe did uranium itself originate? And the answer, when it finally arrives, is so violent and so vast that it makes every human conflict ever recorded look like a minor disagreement. Uranium is not made on Earth. It is not made in stars like our sun either. Our sun fuses hydrogen into helium, helium into carbon, carbon into heavier elements, all the way up the periodic table. But it stops. There is a ceiling. Elements heavier than iron cannot be produced in ordinary stellar fusion. The physics simply does not allow it. So where do they come from? For a long time, this was one of the genuinely open questions in astrophysics. The math said these heavy elements had to be formed somewhere. The universe clearly contained them, but no one could point to a mechanism violent enough to produce them. The answer required detecting something that had never been detected before. Ripples in space-time itself, caused by objects so massive that their collision literally stretched and compressed the fabric of the universe across hundreds of millions of light years. When instruments finally became sensitive enough to catch these signals, and when telescopes were pointed at the source fast enough to catch the light, what scientists saw confirmed the theory. Two neutron stars, each one the collapsed remnant of a massive star that had already lived and exploded, orbiting each other and spiraling inward over millions of years, finally collided. And in the fraction of a second of that impact, a process occurred that no laboratory on Earth can replicate. Atomic nuclei were slammed together with such density, such pressure, that they captured free neutrons faster than those neutrons could decay. In milliseconds, ordinary matter was transformed into the heaviest elements in existence: gold, platinum, and uranium. The cloud of debris from that collision expanded outward through space. Over millions of years, it drifted, cooled, mixed with surrounding gas and dust. Eventually, gravity pulled it inward again. A new solar system began to form. A star ignited at the center, planets condensed from the remaining material, and locked inside the rocks of one particular planet, third from that star. The uranium that had been forged in a catastrophe older than the solar system began to do something quiet and steady and relentless. It began to decay, one atom at a time, releasing heat, warming the planet from within, setting in motion a chain of consequences that would eventually produce oceans, continents, a magnetic field, an atmosphere, and after an almost incomprehensible stretch of time, a technician in a processing facility, staring at a number that does not match. That technician had no idea he was looking at the echo of the most violent event in the known universe. But that is exactly what he was looking at. If this story already has you hooked, do me a favor and subscribe and hit the like button. It genuinely helps this channel and means more stories like this one keep coming. So we have uranium, born in stellar catastrophe, carried to Earth inside the raw material of the planet itself. But here is the part that still gets me every time I think about it. For most of human history, nobody knew it existed. It was sitting in rocks that miners dug up and threw away. Worthless ore. A nuisance. The mineral it hid inside had a name that roughly translated to a miner's curse word, something like false ore or deceiver, because it kept showing up in tunnels where people were hoping to find silver and turned out to be neither silver nor anything else obviously useful. It was heavy, dark, and pointless. So it went on the waste heap. Then a chemist working in a modest laboratory in a northern European city gets his hands on some of this discarded material. He is methodical, patient, the kind of scientist who does not get excited easily. He processes the ore through a series of chemical separations, isolating components one by one, and eventually he ends up with a fine yellow powder, unlike anything he has worked with before. He runs his analysis. It is not any element already on the list. It is something new. He names it after a planet discovered just a few years earlier, the outermost planet then known, sitting at the cold, dark edge of the solar system. Impossibly distant, and only recently found with a telescope. It feels like the right name for something that comes from somewhere beyond ordinary understanding. What he has isolated is not pure metal. It is an oxide, a compound. The actual metal, silvery and extraordinarily dense, almost twice as heavy as lead, does not get isolated until decades later by a French chemist who reduces it from a chloride salt using potassium. When he holds it in his hands, he is holding the densest naturally occurring metal ever extracted. One small block of it weighs as much as a much larger block of iron or copper. It feels wrong, like the world is slightly off its axis when you pick it up. And then something remarkable and slightly absurd happens. Industry gets hold of it, specifically the glass and ceramics industry. Because when uranium oxide is added to molten glass in small quantities, it produces a color. A vivid, warm, yellow-green glow. Under ordinary light, it looks striking. Under ultraviolet light, it becomes something else entirely. A luminous, eerie green that seems to pulse from within the object. Vases, wine glasses, decorative plates, serving bowls. All of them produced in significant quantities and sold across Europe and beyond as fashionable household items. No warning labels, no protective packaging, no precautions of any kind. Because there was no concept yet that this material was doing anything other than sitting there looking beautiful. The uranium in those glasses was decaying the entire time, sending out invisible particles in every direction, passing through the hands of the people who admired them, through the lips of the people who drank from them, through the air of the dining rooms where they sat on display. Nobody felt it. Nobody knew. The concept of radioactivity did not exist. There was no word for what was happening because there was no understanding that anything was happening at all. And that comfortable ignorance lasted until one overcast afternoon, when a scientist trying to study something completely different left a wrapped photographic plate in a drawer next to a uranium sample, came back several days later, and found it had been completely exposed in total darkness, with no light source anywhere nearby. That scientist who found the exposed plate did something that would turn out to be one of the most consequential decisions in the history of science. He shrugged and moved on. Not out of laziness. He was a careful, serious man who had spent years studying how certain materials glow after being exposed to light. He thought what he had found was a strange variation of that same phenomenon. Interesting enough to write a short note about, not interesting enough to drop everything and investigate. He published a brief paper, described the observation accurately, and returned to his main work. The scientific community read it, nodded politely, and also moved on. For nearly 2 years, this observation sat in the literature like a forgotten key on a windowsill. Nobody tried it in any lock. Nobody, except one person. And she did not come from a place of comfort or institutional prestige. She came from a city under foreign occupation, in a country that did not officially exist on any map at that time, divided between 3 empires who had absorbed it and erased its name. She had studied science in secret reading groups organized in apartments because women in her city were barred from universities. She had arrived in a Western European capital with almost no money, speaking the language imperfectly, and had spent her first winter in a rented attic room, so poorly insulated that the water in her washing basin formed a thin layer of ice by morning. She wore her coat indoors to study. She was, by any reasonable measure, not supposed to be there at all. Her name was not famous yet. She was a doctoral student looking for a research topic ambitious enough to matter, but available enough that someone would actually let her pursue it. She came across the published note about the exposed photographic plate. Everyone else had seen a curiosity. She saw an open door. She chose it as her subject. And unlike the man who had made the original observation and set it aside, she decided she was going to measure everything precisely, systematically, and without assumption. She borrowed a sensitive electrical instrument built by her research partner and began testing every uranium compound she could obtain. Not guessing, measuring. The intensity of radiation coming off each sample, recorded carefully. Compared methodically. What she found almost immediately was that the radiation was not coming from the chemical structure of the compound. It did not matter how uranium was combined with other elements. The radiation was a property of the uranium itself, constant, tied to the quantity of uranium present and nothing else. This was not a chemical phenomenon. It was something coming from inside the atom, from a place no one had yet looked. She called it a term she invented herself, drawing from the Latin word for ray. Radioactivity, a word that did not exist before she needed it. And then she did something that nobody expected. She kept measuring, because the numbers were not quite adding up. One particular ore kept producing more radiation than its uranium content alone could explain. A lot more. The excess was too large and too consistent to be an instrument error. Most researchers in her position would have quietly adjusted their methodology until the inconvenient number disappeared. She did the opposite. She wrote down exactly what she found and followed the logic to its only possible conclusion. Something else was in that ore, something unknown, something even more radioactive than uranium itself. She and her partner spent years in a converted shed that leaked when it rained and had no proper ventilation, processing ton after ton of raw ore by hand, breathing the dust, working with materials they did not yet fully understand, isolating concentrates from thousands of kilograms of rock to extract a quantity of new substance so small it could barely be weighed. They found not one new element, but 2. The second one she named after her occupied homeland, the country with no name on any map. It was a scientific discovery and a quiet act of defiance at the same time. She received recognition that no woman in science had received before. And the work that built that recognition left permanent damage in her body that would take decades to become visible. What strikes me most about her story is not the discovery itself. It is the moment she looked at the number that did not fit and decided the number was right and her assumptions were wrong. That single decision, made in a leaking shed by someone who was not supposed to be there, cracked open a door that had been sealed since the beginning of recorded science. Behind that door was the interior of the atom, and nobody yet had any idea how much energy was sitting in there, waiting. Because while she was establishing that radioactivity was a property of the atom itself, physicists elsewhere were trying to figure out what an atom actually looked like from the inside. And a researcher in a stone university building in the north of England was about to run an experiment so simple and so strange that its result would change the entire picture of physical reality. He took a piece of thin metal foil, gold leaf barely thicker than a breath of air, and aimed a beam of tiny particles at it. The expectation, based on everything physics believed at the time, was that the particles would pass straight through with maybe a slight deflection. Matter was understood to be a kind of uniform pudding, dense and evenly distributed. The particles should have sailed through like a needle through fog. Most of them did exactly that, but some of them bounced backward, not deflected sideways, backward, straight back toward the source, as if they had hit something impossibly solid hiding inside the apparently empty foil. The researcher stared at the data and said it was as if he had fired heavy projectiles at a piece of tissue paper, and some of them had come back and hit him. The atom was not a uniform pudding. It was almost entirely empty space, and buried at its center was a nucleus so tiny, so dense, so concentrated that particles bouncing off it flew back the way they came. The mass of the entire atom was packed into a space unimaginably smaller than the atom itself. This researcher understood immediately that if that much mass was compressed into that tiny a space, the forces holding it together had to be extraordinary. And if those forces could somehow be released, the energy involved would be on a scale that chemistry could not even approach. He said so publicly. And then, in the same breath, he said it would almost certainly never be possible to actually access that energy in any practical way. The nucleus was too small, too inaccessible, too well protected by its own electrical charge. Any particle you fired at it would be repelled before it could get close enough to interact. He was one of the greatest scientific minds of his generation. He was completely, catastrophically wrong. But he was wrong only because one specific discovery had not happened yet. A discovery that was sitting just a few years away, already being worked toward in laboratories across Europe, by people who had no idea they were about to hand humanity the most consequential tool it had ever held. The discovery that unlocked everything was made by a man who spent years being ignored, and when he finally found what he was looking for, the world had less than a decade before that discovery ended hundreds of thousands of lives. That is not an exaggeration. That is the straight line from laboratory to consequence, and it ran faster than anyone anticipated. The problem that physicists were stuck on after understanding the nucleus was exactly the one that researcher with the gold foil had identified. The nucleus is positively charged. Every particle available for bombarding it is also charged. Fire a positive particle at a positive nucleus, and the electrical repulsion pushes it away before it ever makes contact. The heavier and more complex the nucleus, the stronger that repulsion becomes. Uranium, the heaviest natural element, had a nucleus so electrically defended that hitting it with conventional particles was like trying to push two magnets together at the same poles. The force just kept pushing back. So the nucleus sat there, dense and inaccessible, packed with energy that nobody could touch. Then a physicist working in a basement laboratory in England found something that had no electrical charge at all. A neutral particle. Not positive, not negative. Just mass with no charge attached. He called it a neutron. And the moment that discovery was published, physicists across Europe and America immediately understood what it meant. A neutral particle does not get repelled. It does not feel the electrical barrier at all. It can walk straight through the defensive field of the nucleus and make direct contact. The lock had been sitting there for years. The neutron was the key. The question now was which door it opened. A physicist in Rome decided to find out systematically. He assembled a team and began bombarding every element in the periodic table with neutrons, working through the list in order, element by element, recording what happened. When lighter elements were hit, the results were clean and interpretable. When he reached uranium, things got complicated. The reaction produced several different radioactive products, and he could not identify all of them clearly. He proposed that he had created elements heavier than uranium, elements that did not exist in nature. It was a reasonable interpretation given what was known at the time. He was awarded the highest recognition in science for this work. And he was wrong about what he had actually done. The correction came from a pair of chemists in a northern European city who repeated his experiments with greater precision. They found barium in the reaction products. Barium is roughly half the atomic weight of uranium. Under every physical model that existed at the time, finding barium there was impossible. You could not fire a small particle at a uranium nucleus and get something half its size. The nucleus was supposed to gain mass, not split in two. One of the chemists wrote a long, confused letter to a colleague he had worked with for many years, a physicist who had been forced out of her position and her country because of her background and was now living in exile in Scandinavia. He trusted her completely. He told her the chemistry was clean, the barium was definitely there, and he had no explanation. She received that letter during a winter visit from her nephew, a young physicist who had traveled to spend the holiday with her. They went walking together in the snow, she moving slowly on skis, he walking beside her through the cold quiet of the pine forest. And somewhere on that walk, between the creak of snow under their feet and the pale light coming through the trees, the answer arrived. The nucleus was not gaining mass, it was dividing. Like a water droplet that stretches and pulls apart under surface tension. The uranium nucleus was splitting into two roughly equal fragments when struck by a neutron. The barium was one of those fragments, and the mass of the two pieces together was slightly less than the mass of the original nucleus plus the neutron. That missing mass did not disappear, it converted into energy. According to a formula that had been sitting in physics for decades without anyone finding a place to apply it, the energy released by that missing mass was enormous. Not chemical enormous, not explosion enormous, something in a completely different category. They worked out the numbers that evening, sitting at a table after they came in from the cold. Using basic arithmetic. The energy released by splitting a single uranium nucleus was millions of times greater than the energy released by any chemical reaction involving a single atom. Millions. That word does not get easier to absorb no matter how many times you read it. One atom. Millions of times more energy than any chemical process. And if splitting one nucleus released neutrons that went on to split neighboring nuclei, and those released more neutrons, and those split more nuclei, the reaction would multiply itself. An avalanche that fed itself. A chain that once started would not need anything from outside to keep accelerating. They published their findings, and the news moved through the physics community at a speed that itself felt like a chain reaction. Within weeks, laboratories across multiple countries were confirming the result. And the people who understood it most completely were not celebrating. Several of them had recently fled countries where the government had decided to restructure society in ways that required removing entire categories of people. They understood, with a clarity that came from personal experience rather than abstract reasoning, exactly what a self-sustaining chain reaction in uranium would mean in the hands of a government with no restraint on its ambitions. One physicist in particular had been thinking about the theoretical possibility of a chain reaction since years before fission was even discovered. He had patented the concept privately and handed the patent to a naval authority specifically so it would be classified and unavailable for others to read in open literature. His colleagues had found this behavior excessive and slightly paranoid. He had not found it excessive at all. And now, with fission confirmed and the chain reaction no longer theoretical, he began moving with an urgency that the rest of the scientific community was only just starting to feel catching up with them. He needed to reach the highest level of government possible. He needed to do it through a voice that would actually be heard. And he knew exactly whose signature on a letter would make a head of state sit down and read every word. The letter that changed the course of history was written by a physicist who was terrified, signed by the most famous scientist alive, and delivered to a head of state who initially had no idea what a neutron was. That is not a joke. That is exactly how the most consequential weapons program in human history began. With a letter, a signature, and a government that needed several months and a small group of advisors just to understand the basic physics being described. The physicist who drafted it had been thinking about chain reactions since before fission was even confirmed. He had watched events unfold in Europe with the specific dread of someone who had already lost everything once to a government that decided certain people were not people. He had left with one suitcase and a head full of physics. Now he was in a new country, watching the same pattern begin to accelerate in the place he had fled. And he knew with absolute certainty that the scientists still working there understood fission just as well as anyone in America or Britain. The question was not whether the physics was possible. The question was who would build it first. He tracked down the most famous scientist in the world at a summer house on the coast, explained the situation in a 2-hour conversation, and watched the older man's face change as the implications landed one by one. The famous scientist later said he had not considered the weapons application at all before that conversation. The letter they produced together was blunt and specific. It described fission, described the chain reaction, described the possibility of a device of extraordinary destructive power, small enough to be transported by boat, and noted that certain European governments had already restricted the export of uranium ore from territories they controlled, which suggested they understood exactly what they were sitting on. The letter reached the head of state and was read. A small advisory committee was formed. The initial funding allocated was so modest it would not have covered the annual salary of a single senior researcher. $6,000. For context, the program that grew from that beginning eventually cost $2 billion and employed 130,000 people across dozens of sites. It became the largest coordinated scientific and industrial effort in recorded history, and almost none of the people working on it knew what the person in the next building was doing. The core scientific team assembled at a remote site in the mountains, isolated by geography and by layers of security that controlled every letter, every phone call, every movement in and out. The physicists brought there included people who had fled occupied countries, people who had left everything behind, people who had watched colleagues disappear. They worked in wooden buildings on a plateau where the wind came off the mountains in the evening with a cold that cut through whatever you were wearing. They ate together, argued in the hallways, scribbled equations on chalkboards that were erased and rewritten daily. The intellectual density of that place was extraordinary. The moral weight of what they were building sat differently on different people, and some of them never found a way to set it down. The first technical obstacle was that natural uranium is a mixture. The isotope that sustains a chain reaction under the right conditions makes up less than 1% of all natural uranium. The rest absorbs neutrons without contributing to the reaction. Separating them was almost impossibly difficult because chemically they are identical. The only difference is a tiny difference in mass. The solution required converting uranium into a gas and pushing it through thousands of membrane barriers, each one producing a microscopic enrichment, thousands of steps to accumulate enough separation to matter. A factory built specifically for this process became, at the time of its construction, the largest enclosed building on Earth by floor area. In parallel, another path was being pursued. Researchers at a university laboratory discovered that when uranium absorbs a neutron and does not split, it transforms through a series of steps into a new element that does not exist in nature in any meaningful quantity. This new element, which they synthesized for the first time in a laboratory using a particle accelerator, turned out to be even more efficient than uranium for sustaining a chain reaction. It was a brilliant solution to the scarcity problem. Nature had provided very little of the isotope needed, but it had provided an ocean of the uranium that could be converted into this new element inside a reactor. Industrial facilities were built near a major river to use the water for cooling, and production began. The first test of a complete device happened in a desert before dawn. The light it produced was visible from hundreds of kilometers away. The heat at the center fused desert sand into a glassy mineral that had never existed on Earth before that moment. One of the scientists watching from a reinforced observation point said nothing for a long time afterward. He had spent years working toward this result. Standing there in the pre-dawn silence with the light fading from the sky, he later said what he felt was not pride and not triumph. It was something closer to the sickening recognition that the world had just divided permanently into before and after, and there was no way back across that line. Two devices were used against cities within weeks of that test. The first used uranium. The second used the new synthesized element. Together they ended a war and opened an era that nobody had a framework for yet. An era in which the most powerful nations on Earth pointed weapons at each other that could not be used without consequences that circled back to destroy the one who used them. The element that had been thrown on a waste heap by miners who thought it was worthless had just rearranged the entire structure of global power. And that was only the most visible thing it had done, because while governments were building arsenals and drawing up strategic plans, a much quieter conversation was beginning among a different group of engineers. They had looked at the same physics, at the same chain reaction, at the same extraordinary density of energy in uranium, and they had asked a completely different question. What if, instead of releasing all of that energy in a single uncontrolled instant, you released it slowly, steadily, in a controlled and sustained way? What if the chain reaction, instead of being a detonation, was a furnace? The first time electricity was generated from nuclear fission, it powered 4 light bulbs. 4. The engineers in the room reportedly stood and watched those 4 bulbs glow with an attention they would normally reserve for something much more dramatic. But they understood what those 4 bulbs meant. That same reaction that had flattened cities could now illuminate a room. And if it could illuminate a room, it could illuminate a city. And if it could illuminate a city, it could power an entire civilization without burning a single gram of coal or releasing a single breath of smoke into the air. The peaceful application of the same physics seemed, in those early years, like it might be the redemption of everything the weapons program had done. Like the story might still have a decent ending. It did not go quite that smoothly. And the reason why brings us to 3 places, 3 different decades, 3 very different failures, and one statistical fact that almost nobody knows because it is far too quiet and far too undramatic to compete with the images that replaced it in public memory. 3 major nuclear accidents happened across 3 different countries in 3 different decades, and every single time the public reaction was so enormous that it reshaped energy policy for a generation. But here is the number that almost never gets mentioned in the same conversation. Across its entire history, including every accident ever recorded, nuclear power causes fewer deaths per unit of energy produced than coal, oil, gas, and in most studies, even fewer than some sources we consider completely safe. That fact is sitting in peer-reviewed journals. It is not secret. It is just very quiet. And quiet facts lose every time they compete with images of cooling towers and evacuation buses on the evening news. The first accident happened at a plant in Pennsylvania when a failure in the water supply system triggered a cascade of smaller failures that partially exposed the reactor core. Some radioactive gas was released. The surrounding population was gripped by fear intense enough that the state governor recommended evacuating pregnant women and young children from the immediate area. Subsequent studies, spanning decades, found no measurable increase in illness among people who lived nearby. The damage was almost entirely economic and psychological. But in the years that followed, not a single new reactor construction permit was issued in that country for over 3 decades. 30 years of a technology standing still because of an accident that, by the data, harmed almost no one physically. The second accident was genuinely severe. A reactor in the Soviet Union failed catastrophically during a safety test that was conducted under conditions no sane operational protocol would have allowed. The reactor design had a fundamental flaw that made it accelerate rather than slow down as it overheated. A fire burned in the reactor's carbon moderator blocks for days, carrying radioactive particles high into the atmosphere, where wind distributed them across hundreds of kilometers. The confirmed deaths directly caused by the accident were measured in dozens. Long-term cancer estimates in the most exposed populations run into the thousands. It was a real disaster caused by a specific design flaw that most reactors in the world did not share, combined with institutional pressure that overrode basic safety judgment. It was also, in public imagination, transformed into something closer to the end of the world. An image that stuck and spread and became the lens through which nuclear energy was viewed everywhere. The third accident happened when a massive earthquake and the wave it generated knocked out the emergency cooling systems at a coastal plant in Japan. 3 reactor cores melted. It was the most serious nuclear accident since the Soviet disaster. According to researchers and international health organizations, the number of confirmed deaths from radiation exposure was 0. The evacuation itself, the disruption to tens of thousands of elderly and seriously ill people, caused more measurable harm than the radiation did. Meanwhile, the wave that triggered everything killed roughly 18,000 people in a single afternoon. A number that received a fraction of the ongoing attention directed at the nuclear facility it had also struck. I am not telling you nuclear accidents do not matter. I am telling you that the gap between how dangerous nuclear power actually is and how dangerous we feel it is may be one of the largest mismatches between data and emotion in modern public life. And that mismatch has consequences. Because while governments were stepping back from nuclear construction, the carbon that was not produced by those reactors was being produced by something else instead. Now here is where the story takes a turn that almost nobody expects. Because while all of this was happening above ground, something extraordinary was quietly discovered beneath it. Geologists examining ore samples from a deposit in West Africa found that the isotopic composition of the uranium was wrong. The same way that technician at the beginning of this story found a number that did not match. The uranium had less of one particular isotope than it should. Investigation revealed that approximately 2 billion years ago, a natural nuclear chain reaction had spontaneously started inside the rock and run continuously for hundreds of thousands of years. No engineers, no blueprints, no control rods. Just uranium ore, groundwater acting as a natural moderator, and the physics doing exactly what the physics does when the conditions are right. 16 separate reaction zones were eventually identified at the site. Nature had built a nuclear reactor and run it until the fuel concentration dropped too low to sustain the reaction. Then shut it down automatically. The researchers then asked where the radioactive waste products from 2 billion years of fission had gone. They looked. The waste had moved, in most cases, only a few meters from where it was produced. The surrounding rock had held it in place across 2 billion years of geological time. This observation became one of the most important pieces of evidence in the argument for burying nuclear waste deep underground in stable rock formations. Nature had already run the experiment. The results were published not in a paper, but in the geology of an African hillside. The waste problem is real, and it deserves honest discussion. Spent nuclear fuel contains dozens of radioactive isotopes with half-lives that range from 30 years to millions of years. By the early 2020s, the world had accumulated roughly 400,000 tons of it, most sitting in temporary storage at reactor sites. The only solution, with genuine scientific consensus behind it, is deep geological burial, placing the waste in stable rock hundreds of meters underground and sealing it permanently. One Scandinavian country is the only place on Earth actually doing this. The tunnels are being cut into granite on a coastal island, designed to isolate the material for 100,000 years. 100,000 years. That is 10 times longer than all of recorded human history. The engineers faced a problem with no precedent. How do you warn people 100,000 years from now not to dig in a particular spot? Languages die. Alphabets become unreadable. Civilizations rise and collapse and are forgotten. 100,000 years ago, our ancestors were still living entirely by hunting and gathering. There is no cultural continuity across that kind of time. Linguists and anthropologists and communication theorists were brought in to study the problem. Nobody found a solution that anyone could honestly call reliable. Humanity has, for the first time, created something that requires a warning extending beyond the horizon of any civilization that has ever existed. That is not a metaphor. That is a literal engineering problem that remains unsolved. And yet, uranium keeps giving. Right now. Inside the Earth, beneath your feet, uranium is decaying, slowly, steadily, the same way it has been decaying since before the planet solidified. That decay releases heat. About half of the heat flowing outward from the Earth's interior comes from this radioactive decay, primarily from uranium and two other long-lived isotopes in the rock. That heat drives the slow, churning movement of the mantle. That movement drives plate tectonics. Plate tectonics builds mountain ranges, feeds volcanoes, cycles carbon through the atmosphere, and keeps the planet geologically alive. The churning also maintains the liquid iron outer core that generates the magnetic field surrounding the Earth. That magnetic field deflects the stream of charged particles coming from the sun. Without it, those particles would gradually strip away the atmosphere the way they stripped away the atmosphere of Mars, leaving behind a cold, airless, dead surface. Uranium is one of the reasons this planet is habitable. Not metaphorically, physically, measurably, directly. In hospitals around the world right now, tens of millions of patients every year undergo diagnostic scans using an isotope produced directly from uranium fission in a reactor. The isotope has a half-life of 6 hours, which means it delivers a clear signal and then leaves the body quickly without accumulating in tissue. It shows doctors not the structure of an organ, but its function. How blood moves through the heart, where a tumor is consuming more energy than surrounding tissue, where a kidney is failing to process what it should. It has no natural source. It cannot be stockpiled. Every batch has to be produced fresh in a nuclear reactor and delivered within hours. Every day that supply chain functions, cancers are caught earlier, and heart conditions are identified before they become fatal. The chain runs directly from a uranium target in a reactor to a scan result that saves a life. Most patients have no idea. And traveling through interstellar space right now, beyond the edge of the solar system, are two probes launched nearly 50 years ago. They are further from Earth than any human-made object has ever been, more than 23 billion kilometers from the Sun. Their instruments are still running. They are still sending data. They are powered by the heat of radioactive decay, converted to electricity by a system with no moving parts. The element used in those generators is produced in reactors by irradiating a material that itself accumulates in reactors running on uranium. The chain goes from uranium ore to reactor to isotope production to a generator to a signal arriving on Earth from interstellar space. One element, that chain. Uranium can also tell time in a way nothing else can. It decays into lead at a rate so stable and so immune to any external condition, any temperature, any pressure, any chemical environment, that by measuring the ratio of uranium remaining to lead accumulated in an ancient mineral crystal, scientists can calculate with an error of less than 1% how long ago that crystal formed. This is how the age of the Earth was determined. Ancient crystals from a remote region of Australia were found to be 4.4 billion years old. Combined with analysis of meteorites and samples from other bodies in the solar system, this method established the age of the solar system itself at 4.567 billion years. We know the age of our planet to within 1% because uranium decays on a schedule that nothing in the universe can interrupt or adjust. And that brings me to what I think this whole story is actually about. Uranium does not have intentions. It does not care what we build with it or what we leave in the ground because of it. It has been decaying at the same rate since before the sun ignited. It will still be decaying at that same rate long after every city on Earth has been buried under geology. The physics does not negotiate. It does not respond to fear or policy or public opinion. It just runs. What changes, the only thing that has ever changed in this entire story, is what we understand and what we choose to do with that understanding. Every chapter of this story, from the woman in the leaking shed to the 4 glowing light bulbs to the unsolvable warning problem in the Finnish granite, is a chapter about that gap between what the physics makes possible and how well human judgment has risen to meet it. So here is the question I want you to sit with. Uranium has given us the tools to destroy civilizations and the tools to power them cleanly, to heat the planet from within and to diagnose cancer in the body, to measure the age of the world and to travel beyond it. We have had all of this for less than 100 years. Given everything you just heard, do you think humanity is ready to handle what uranium makes possible? Or are we still running on instinct while the physics runs on schedule? Write your answer in the comments. I genuinely want to know what you think. And if this story made you see something differently, hit the like button and subscribe. More stories like this one are coming, and you do not want to miss them.